In this video, I'm going to go over an example of how to calculate the shear force diagram and bending moment diagram for a beam with an internal release. So here's a propped cantilever that has an internal hinge. The hinge on the inside provides one extra equation of condition, meaning that this is a determinate system. So we can solve the bending moment diagram and the shear force diagram without needing to resort to anything other than the equations of equilibrium. So we'll just get started. The first step is, as usual, to find the reactions. So since this has a hinge inside, we're going to have to use a free body diagram of the cut system on the right of the hinge or on the left of the hinge in order to find these reactions, in order to get access to that extra equation of condition. So we'll start with an FBD of the right side of the hinge. Okay, and it's going to look something like this. So here's our beam. We have reaction forces. So this is the reaction forces from the hinge, since we've cut it. So this is the reaction of the other side of the beam on the right side of the beam. And then on the right side, we have a vertical reaction only due to the roller support here. And then we have this distributed load on top that only goes up to the point 4 meters from the left. And this is 4 kilonewtons per meter. And then, as we already see above, this is 4 meters on the left and 2 meters on the right. So the reason that I chose the right side is because there's a lot less going on and there's only one reaction force. This is going to make it very easy for us to use the sum of moments to directly solve for Cy. So let's go ahead and do that. So if I take the sum of the moments about point C, so Cy and Ey. Actually, Ey is the one that's more important. So here we have, if we assume that counterclockwise is positive about C, then the distributed load provides a clockwise rotation, which is negative 4 kilonewtons per meter, times the length of that load, distributed load, which is 4, times the center where it acts at 2 meters. And then we have plus, because Ey acts counterclockwise, Ey times 6 meters, which is the distance from C, equals 0. And then if we solve this equation, we easily get Ey is 5.33 kilonewtons. And since this is positive, it's in the same direction as we've drawn it, which means that it is up. Okay, so that's Ey. We don't really need to solve for Cy here, but I'd like to do it because I can use it later, just as a check. So we get sum of Fy is 0, therefore Cy is up, that's positive, minus 4 times 4, which is from the distributed load, plus 5.33, which is the reaction we just solved for, and that's up, so it's positive. So then we solve easily. Cy is 10.67 kilonewtons. It's positive, so it's the same direction we've drawn it, which is up. Okay. So then from there, we can use the full free body diagram to solve for the rest of the reactions. Okay, so let's quickly draw that system. Okay, so we've got Ey on the right, which equals 5.33, which we just found. We have our distributed load. It's good practice to just draw out these full free body diagrams so that you don't miss it, so you don't miss anything. Helps you to keep track. So here's Ay, we have Ax. These are our reaction points at the fixed end. And since this is a fixed end, we also have a rotation. And that one, like this, is Ma. Now I've drawn this in the clockwise direction, which which we can say is a positive rotation. But actually this would create negative bending, this MA. So you have to just watch your sign convention. But anyway, whatever you choose, just make sure to be consistent. So this is 4 kilonewtons per meter. And then we have a vertical load somewhere over here that's 10 kilonewtons. And then I'll draw, we have a point moment, a clockwise point moment at this point, same point as the point load of 2 kilonewton meters. Just draw that in a different color so it's easier to see. And then don't forget we have this hinge that's over here. Okay, so I'll leave the dimensions out because you can refer to the drawing at the top. So if we do sum of moments about A now equals 0, we'll say clockwise, counterclockwise is positive. Then first of all, this force MA, which is the reaction force, is in the positive direction, clockwise. Then we have minus 2 kilonewtons, 2 kilonewton meters. This is the point load. Again, you'll recall that it doesn't matter where this point load acts along the beam. It's just added to the moment equilibrium as a constant. So since it's clockwise, it's negative, and we just put 2 kilonewton meters. Then we have negative 10 times 2, that's for this point load, and this is 2 meters between A and the point load location at B. We have 4 times 8, which is the length of the distribution, times 4, which is the distance to the center of that distribution. And then that's negative because it's clockwise, and then plus for this counterclockwise reaction force, F.5.33 times 10 meters, which is the total length of the beam, equals 0. So we can solve for MA, which is the fixed end reaction, moment reaction force, and that comes out to 96.7 kilonewton meters. And since this ended up being positive, it's in the same direction that we've drawn it, which is counterclockwise. Okay. Then just finishing up for our reactions, we've got sum of y in the positive direction equals 0. So now we've got AY is up, minus 10 for the point load, minus 4 times 8 for the distributed load, plus 5.33 for the reaction, and that equals 0. So AY is equal to 36.7 kilonewtons. It ended up being positive, so therefore it's up. And lastly, the easiest one, sum fx, say right is positive equals 0. There's only one load in the x direction, which is AX, the reaction. And since there's no other loads in that direction, AX is just equal to 0. So that's it. That's the reaction. And that's basically all of the information that we need for this determinate system in order to start drawing our shear and moment diagrams. So let's go to the next page here. Okay, so we're ready to draw shear force diagram. Okay, so let's use a horizontal line to represent our beam. I'll try to do these things to scale. 2 meters, 2 meters, 2 meters, 2 meters. Okay. And this is our shear force diagram, which usually I'll write a little V. You can put the units out there so you don't have to put them at every location. Or sometimes this could be also S. Okay. So first, so what we do when we're drawing the shear force diagram is we're just going to start at the left. If you look at our full free body diagram, every load that pushes up, our shear force diagram will go up. Every load that pushes down, like this distributed load and this point load, will push our shear force diagram down. The distributed loads push them down incrementally, so that's why we get kind of a linear change on the shear force diagram, whereas the point loads make a step function. Point moments, however, don't have any effect on the shear force diagram. So if we start from the left, we go up by AY, which is 36.7 kilonewtons. So we just draw up. We start at 0. We draw up. that's relatively up. Okay, that doesn't want to erase. Okay, so we draw up a straight line, and at the top, this is equal to 36.7. Okay, so this is like I've gone up AY. These things in red you don't have to draw on the shear force diagram. I'm just drawing them for clarity. So then in between, in between A, this is point A, this is point B, right? This is C, D, E. In between point A and B, we have this distributed load that changes the shear force by 4 kilonewtons per every meter. So that means in between A and B, there's 2 meters, so it's going to go down by 8. So I can draw the point here where it ends up. This is maybe around here. Now you can draw these to scale, and that would actually help a lot, but that's quite difficult to do on the computer. So if I subtract 8, that's 28.7. Now this is a linear change. Because we have the distributed load, so each meter we're going down by 4. That's 4 kilonewtons per meter. Or each millimeter we're going down by 4 divided by 1,000. And this slope here is equal to 4. Okay. Now then at B, we have a point load that pushes down by 10. So that means our shear force diagram is going to go down by another 10. And that's going to end up about here. So that's going to be point 18.7. So you got to make sure to label all the points on the shear force diagram. And so again, this has gone down by 10 due to that point load. Now to the right, we're just going to keep going down by 4 kilonewtons per meter until we reach point D. Now we can find out what the shear force is going to be at point D by starting with what it is at point B, and then subtracting 4 times 6, which is the distance in between them, 4 times 6. Okay, so if we subtract that, we can find out that at D, we're going to have about 5.3. Okay, so that's 18.7, which is the starting shear at B. This is point B, A, this is D, and this is E, right? So we know that if we subtract 4 kilonewtons per meter times the distance here, we're going to end up at negative 5.3, which just means that it's on the other side of the shear force diagram. And so now I can draw my line. I've got to draw it a little bit shallower. So again, this slope, let's see that ended up properly here. This slope is the same as this slope because it's the same distributed load. So this is also 4, slope of 4 to 1, right? 4 to 1. Okay. Now what happens at that hinge location, which is C here? Well, at that hinge location, the shear force diagram is not affected directly by the existence of the hinge, because that hinge transmits vertical load, so it also transmits shear. But we did calculate what the shear force is in the beam at C, because when we did our cut, we found what CY is, and CY, since this is a cut, is equivalent to the shear force that's transmitted through the hinge, and that force is 10.67. So this value here, the shear force at C, has to be equal to 10.67. And we know that that's true because if we follow this line, 4, with the slope of 4, that means we subtract 4 kilonewtons per every meter, and there's 2 meters between B and C, so we're subtracting 8. So 18.7 minus 8 is 10.7, or about 10.67. Okay, so we've confirmed this number independently multiple ways. Okay, and then so from D, we don't have any change. So there's no forces between D and E. no external forces. So that means that the shear force diagram between D and E is going to remain constant at that level of shear. I got to move this out of the way a little bit. Okay, so it's constant across, and that's 5.3 as we said. And then once we get to E, the force pushes up, so that means our shear force diagram goes up from this reaction force, which is 5.3. So that brings us back to 0. Okay, and in our shear force diagrams, this is 5.3, in our shear force diagrams, we always have to end up back at 0 once we get to the end. So that's a good way to check that your reactions are correct. Now if we ended up at plus 10, then we know that we have a problem. Now because of your because of the way that you might have rounded some of the numbers along the way, you might not end up at exactly 0. You might end up at 0.1 or negative 0.1, and that's okay. But any significant change, any significant difference here, and you've probably made a mistake. So I'll put a little note here. Ends at 0. Okay, and it does. Now another thing that we might want to know in this shear force diagram is where does this location lie? Because when we have a point of 0 shear, that means the slope of our moment diagram is 0. And so points where the slope of our moment diagram is 0 can tend to be locations where we have local maxima or minima in the moment diagram. So it's useful to know what this point is. Now how do we find what this point is? Well, it's pretty easy. So we look at, we want to find what this distance is. Okay. So using similar triangles, okay, we know the total distance here. Okay, we know that this total distance is 4 meters between C and D. Okay, so this is not drawn to scale, but you can see this triangle has a height of 10.67. This triangle has a height of 5.3. So actually this should look on the diagram higher than this one. The way I've drawn it, I haven't really drawn it to scale, so that doesn't really reflect to be the case. And then since these two triangles here are similar, they have the same angle, okay, this theta equals this theta because the slope is the same for both, then we can relate x1 here and x2 here to the heights. Okay, so what we can do is we can say that x1 over 10.67 equals x2 over 5.3. And so if we want to find x1 in terms of, let's find x2 in terms of x1. So x2 then is equal to 0.5 x1. Okay, and therefore this total distance here, which is 4 meters, is x1 plus x2. So x1 plus x2 equals 4. x1 plus 0.5, x1 equals 4. So we can find that x1 is equal to 2.67 meters. Great, so now we know where that maximum is. So you can see obviously that's more than halfway between C and D, so it's actually somewhere over here. Now if you drew these exactly to scale on graph paper and used a ruler, then that would come out and you could just measure it. Okay, so now we know the full shear force diagram. Okay, so let's find the moment diagram. Okay, I'm going to say that that's M. Okay, and I'll put the units here, kilonewton meters. Okay, so I'm going to draw this somewhere about here. Okay, so let's draw our beam. Okay, that's E, this is A. Okay, so how do we start drawing the moment diagram? Well, okay, the moment diagram is basically equal to the area of the shear force diagram as you move across, except for the fact that wherever there's a point moment, like at a reaction here, we've got a point moment at the end, or this applied point moment that we have on our system, that makes the moment diagram jump. Okay, and a counterclockwise moment makes it jump down, and a clockwise moment makes it jump up. So we start here with our point moment at the end, MA, which is 96.7. This is counterclockwise, therefore it's going to jump down. So let's draw, we go down, 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 to about 96.7 kilonewton meters. So this is because we have MA, and that's counterclockwise, so it goes down. Okay, so now every area here changes the moment diagram by an amount equal to the area. So if I want to find the moment at B, I start with the moment at A, which is 96.7, and then I'm going to add whatever area is in the shear force diagram between A and B, which is this trapezoidal shape here. Okay, so if I solve that, then I find that at B, my moment is equal to 31.3. So here's B. It's about a third of the way, so it's about here. Okay, and this is 31.3. But now, how does the moment diagram change in between these 2 points? Well, you have to always remember that the value of the shear force diagram is equal to the slope of the moment diagram. Okay, so higher numbers mean a steeper slope, lower numbers mean a shallower slope. So at 28.7, we have a shallower slope than we do at 36.7. So we get something that, so we have a steeper slope here, and we have a shallower slope here. Okay, and so the shape that's going to join those is going to be a parabola that joins these two. So whenever you have a linear change on the shear force diagram, that equates to a parabolic change on the moment diagram, because the moment diagram is basically an integration of the shear force diagram, which makes sense. That's why we're counting the areas, because we're integrating the areas into the moment. So when you integrate a straight line, you get a parabola. If the shear force diagram is constant, then when you integrate it, you get a straight line on the moment diagram. And if the shear force diagram has a parabola on it, then the moment diagram is going to be a cubic. Okay, so we can draw the shape here. Okay, approximately, it's going to look something like this. Okay, so we know that it has to change, something like that. Alright, we could find the point, we could find every point here if we liked, or we could find the shear force diagram in terms of the distance x from the left. So we could find the equation of this line on the shear force diagram and then integrate it, and that would give us the shape of the moment diagram. Okay, so that gets us to point B. Now at point B, we have a point moment, and this is a clockwise point moment. And a clockwise point moment moves us up on the moment diagram. So it ends up with a shift up. And here I'm going to exaggerate it a little bit because it's quite small. We have a shift up of 2 kilonewton meters, which is the value of the shear moment, which is the value of the point moment, and that brings us to 29.3. Okay, so here we have a shift up of 2 kilonewton meters, and that's because that's clockwise, so that goes up. Okay, so now for the rest of this, we are going to continue to integrate these areas. Now, one interesting thing, we know that at the hinge, which is at C, our moment has to be equal to 0. So if we start at 29.3 and then we add this area, this trapezoid, we should get down to 0. And indeed that's what happens. So if you take the area of this trapezoid, right, and you'll recall, area of a trapezoid right, is equal to the average height of the trapezoid times the width. Okay, so the average height is 18.7 plus 10.67 divided by 2 times 2, because that's the width. So it's basically 18.7 plus 10.67, which is equal to 29.3. So we know that we have we're going to get back to 0 here. So that's just another check. Another check to show that what we're doing makes sense, because we know that the moment at the hinge has to be 0. I'm just going to fix this a little bit. Okay. So this parabola is basically a continuation of this parabola, except shifted up. And we know that this has to be 0 here. Hinge. Okay. And so from now on, we have our maximum point. So you see our slope was still decreasing between B and C, so that means our slope is decreasing. We have a higher slope here and a lower slope here. And then when we get to this point, our slope is going to be equal to 0. And the value of that is going to be 0 plus the area of this little triangle. And so this is 10.67, right, divided by 2 times the distance here, 2.67, and we're going to get about 14.3. And we know that the slope here is 0, because wherever the shear force diagram is equal to 0, the slope of the moment diagram is equal to 0. So this is the peak of our parabola. And then from there, we start subtracting from the moment diagram. So anything on the bottom of the shear force diagram is a negative shear, and that starts subtracting from the value of the moment diagram. So we start at 14.3, which is our location of 0 slope. And when we get to D, we're going to subtract 5.3 divided by 2, so it's the area of this triangle. 5.3 divided by 2 times this distance, which is 4 meters, minus 2.67. And what we're going to get is 10.8. And this is in the shape, still in the shape of a parabola, which is hard to see because it's quite small. Okay, so that's like a parabola. Okay, and then what happens between D and E? Well, D and E is constant, so that means that we're going to get a linear change on the moment diagram. And we're going to get a value of 5.3 times the distance, which is simply the area underneath this, and that's 5.3 times 2, which is equal to 10.6. Which you see is not quite equal to 10.8, so this is an example of where the round-off error has kind of moved us away from 0 once we get to the end. Now, what I really should do is maybe keep a few extra digits in your values as you're going through the construction of the moment diagram. So instead of just using 3 significant figures, use 4 or use 5, and then by the time you get to the end, then everything should add up. And then when you're asked to quote the numbers, just make sure to quote them in the appropriate amount of significant figures. So when you draw your final moment diagram, you're probably going to want to just use the 3 or the 3.5. So then this is going to be a straight progression, which is reducing the moment based on the incremental area, and this gets us back to 0. Okay, and this slope, this has a slope of 5.3. Okay, which is linear. And this is a parabola. Oops. Parabola. And that's it. That's the full moment diagram. So now we know everything. We should also signify where this point is. There's 2.67 because it's not at one of these locations. So this is A, this is B, this is C, this is D, and this is E. It's good to label these locations so that we can refer to the dimensions on the main drawing. So let's shear a moment diagram. Now as a final step, let's try to draw the displaced shape of this system. This is pretty straightforward to do when you actually know the moment diagram. So we have our wall. Okay, and now let's just draw our undisplaced, our undeformed shape here, which just goes all the way to here. And this is where we have our roller. Okay, so we know that we need a horizontal. Let me draw it in a different color. We know that we need to have zero slope at the fixed end. So the fixed end has to be 90 degrees. We know that. Okay. Also, we know that the deflection has to be equal to 0 at the pin, because the pin can't move up and down. So we know our beam has to end up here. So when we have moment on the bottom of the beam, or sorry, if we have negative moment here, we know that this represents concave down, a concave down shape, based on the conventions that we've used. So negative moment here on the bottom of the moment diagram, as long as you draw it this way, where up shear moves the moment diagram up and down shear moves the moment diagram down, and the shear is constructed by the reactions in the way that we did it, then this is concave down and this is concave up. Okay, so we know that the shape of this is going to be down until we get to point C, and then the shape is going to be up. Okay, so we know that this has to bend downwards, and we know that this has to bend upwards. And we know that point C is going to be displaced downwards, right? So point C is going to be somewhere down here. So if we continue to draw this shape, this is effectively a cantilever, right? And it bends concave down the whole time between A and C. So we know that it has to bend something like this. Let's try to draw it again. Okay, we know it has to bend something like this. I want to draw it a little bit more bendy. Okay, like that. Good. Okay, so it bends downward until it gets to point C. Okay, and then from there, it's always bending upwards. And at the 0 point, we have neither concave down nor concave up. And what this really means is we have a moment release at the hinge. Okay, so since we have that moment release, we can actually have a discontinuity in the shape of the beam. Okay, so this does not have to be continuous because it's released for a moment. So it's just like a regular hinge that you would have in a door. So then we know we have 0 here, and this is concave up the whole time. Maximum concavity in the middle, and then it straightens out as it gets to the pin. So this is our displaced shape. And remember, this is a hinge. So that's why we have this discontinuity in the shape of the beam, because we have this hinge here. And that's the displaced shape of the system. And that is how you draw a moment diagram.